We know that the universe is expanding. We've known that for almost 100 years. The rate at which the universe expands is a number we refer to as the Hubble Constant. When Hubble was launched, one of its main objectives was to measure the Hubble Constant, the expansion rate of the universe, by resolving individual stars in distant galaxies. Hubble was really the first telescope that allowed us to easily resolve the individual components, the stars, in a distant galaxy to gauge its distance. And that's part of the ingredients you need to measure the expansion rate of the universe. Over time, Hubble also was improved by a series of servicing missions that increased the sensitivity, resolution, and also ultimately allowed us to make observations in the near-infrared, which reduces the effects of dust. Dust is scattered throughout the universe, and if you're looking at a distant light and trying to tell how far away it is, dust can dim the light and fool you into thinking it's further away than it is. Hubble has sort of all of these tools on its utility belt that allow us to measure the expansion rate as well as it's been measured to date. Hubble found that the expansion rate of the universe is speeding up, it's accelerating due to a new component of the universe that we call dark energy. Dark energy actually reverses the sign of gravity. It actually gives rise to a repulsive gravity, which sounds very strange, and it's not something that Isaac Newton would have understood, but it is a feature in Einstein's theory of general relativity, Einstein's theory of gravity, that replaced Newton's theory of gravity. And in that theory, you can have such a material. If you have a constant energy in empty space that's unavoidable, then it will give rise to this repulsive gravity. Because gravity is weakest in the empty regions of space between galaxies, dark energy has its most pronounced effect in deep space. It's driving, now pushing the universe to expand faster and faster. The James Webb Space Telescope has certain capabilities that are even greater than Hubble's. It will have greater resolution. It can extend observations further to the infrared to even further diminish the impact of dust. So it will both simultaneously give us a sharper view of these distant stars that are used to calibrate the expansion of the universe, and it will also allow us to see through the last little wisps of dust in front of those. Our goal is to measure the Hubble constant to 1% precision, and so we are using the Hubble Space Telescope and James Webb Space Telescope to refine those measurements and to learn about the equation of state of dark energy.